Swayam Prabha. Digital India. Educated India.
In this lecture, we will cover the topic of shear flow in thin-walled sections. Now, what do we mean by thin-walled sections? Now, thin-walled sections are those for which the thickness of the members are much thinner or much lesser compared to the overall dimensions. A classic example of thin-walled section is essentially steel sections, which are used in steel construction, used in bridges as well as in steel buildings. For example, warehouses and so on. These thin-walled sections play a very important role in the construction. I have a thin-walled section over here. So you see, this is an example of a thin-walled section where you see the overall dimensions, this thickness or the thickness of the top part is known as the flange, this is known as the web, this is known as the flange again. So the overall thickness, this thickness as well as this thickness and this thickness, the thickness that you see over here, they are actually quite small compared to if you compare it to the overall dimensions of the structure. So we will learn that how the shear stresses and the shear flows, it happens in thin-walled sections, and you will see on an initial glance it will appear to you as quite non-intuitive, but hopefully with the understanding of how the flow of shear or how the shear stresses develop in these thin-walled sections, you will be able to appreciate it a lot more than someone who is not exposed to the concepts of shear forces or the shear flow in thin-walled members, right? So that is essentially our topic of discussion today. So we are going to talk about the thin-walled section. So let me just turn on my pen over here. So thin-walled section. So this constitutes our topic of discussion today. Right. So now if you look at thin-walled sections, before we begin in looking into the shear flow of thin-walled sections and so on, first let's see that what is going to be our saving grace for this one, that why are some of the flow, as you can see here already a bit like how the flow of shear and everything happens, but what is our saving grace for this one? The saving grace for learning about thin-walled section is essentially something which you have already seen, right? Number one is the complementarity of shear, an idea to which you're already exposed to and you know pretty well, which essentially means that if you have a shear developing in one of the faces, on the corresponding perpendicular face over here, you have an equal and opposite shear that develops. So that essentially we had used this very idea itself to derive the shear formula initially. Now this just shows in one of the faces. In this face over here, you can have complementary shear in the other faces as well, something like this. For example, if you have a shear stress here, you will have a complementary shear in all across these four sides. Or if you're having this this vertical slide, if you have shear in one of the faces, automatically the shear develops in the other faces to maintain the equilibrium of forces and the equilibrium of moments. Now one more important thing which is somehow related to complementarity as well, if you remember when we had talked about these rectangular beams, what did we see in this one? In this one we saw that the shear stresses are zero or negligible at the top and at the bottom, whereas the maximum shear stresses, the vertically down shear stresses, happens at the center, at the neutral axis. Now focusing on the top and the bottom, the formulation works out like that, and also intuitively you remember that the shear stresses here are essentially negligible or zero, simply because you do not have any shear on the top. So if you do not have any shear over here, complementary to that is the shear here, something like this. If you have one tau over here, you will have an equal complementary shear here, but here you have on the top surface, you do not have any shear, so the complementary shear will be zero. Similar to what you see here in the thin-walled sections, which you will see that if you have, right, if in this kind of a section, right, if you have a shear force which is acting from across the surface, see here on the top it is essentially free of any load. So if it is free of any kind of shear that is there, so that means that there is going to be a negligible amount of shear in this direction, simply because here there is no shear, so no complementary shear develops over here. Similarly, here in these faces, in these side faces that you see over here, if there is negligible amount of shear, if there is no shear externally applied, no surface load which is over here, correspondingly, since this is negligibly zero, this is also going to be negligibly zero, but you will have some vertical shear over here simply because the member is long and elongated, right? So you see that this complementarity of shear will play a critical role. So just keep in mind what we discussed. Since the shear here is 0, this shear will more or less be 0, this vertical component. Since here the shear is 0, this horizontal component for the web part will be 0. So this is the top, this is the flange, and this is the web, and this is the flange again. We'll write it out to, to have the terminologies particularly clear as well. Now the other saving grace in addition to complementarity of shear is something which you are also familiar with, which is the shear flow. Now remember, we had discussed the shear flow is nothing but the shear force per unit length. And how is that obtained? You multiply the shear stress, that is the tau that you have, with the thickness T of the member to get the shear flow. And the unit of shear flow, since tau is Newton per mm square, remember the unit of shear flow, since you're multiplying with one element of dimension, it's going to be Newton per meter or pound per inch and so on, right? And also tau, remember, is VQ by I times T. So since you're pulling this T over here, Q becomes equals to VQ divided by I. Okay, now with these concepts being clear, the complementarity of the shear and what is the shear flow, let's go ahead and look at some thin walled sections. So the first thin walled section which we are going to look at is this I section over here. So see, this is what we wrote, that the top part which you see over here is known as the flange. This bottom part is also the flange, and in between what you have is known as the web. So these are very common terminologies in these thin walled I sections that you see. Now what I want you to do is essentially focus on one small element over here. So suppose you take this dark gray portion that you see over here. See, in this part, as I said, that in the top part, in the top face of your section, essentially the top face of your section, the shear is 0. So that essentially means this particular shear is 0. This vertical component is more or less 0 over there. Now, but one very important thing, you see, this beam is subjected to this M and M plus dm over here. Now because of this M and M plus dm, because of this moment, you are going to have those normal stresses. Remember, sigma equals to my by I. Now where are these stresses maximum? It is always maximum at the top and the bottom. So for here, if I am having a moment, the stresses, the normal stresses is going to be highest over here as well as over here, maybe tension or compression depending upon the nature of the moment. So if there is a difference of the stresses or the difference of the forces, because you have M over here, M plus dm over here, what takes that particular shear? What is resisting? If I'm saying that this kind of amount of this member is very thin and the shear acting along this is 0, so what essentially takes that shear? Let's go ahead and take a look. Now for this member, if you write it out, this is essentially how it happens. So if you take this particular section and say, because of sigma equals to that M by I, my by I, or M plus dm times y over I, as a result of which, maybe this is part of this entire triangular force that you have. Here you have F plus df and here you have F over here. Essentially the force which is resisting, if you write the force equilibrium again, what actually happens is that if you take a small strip over there, this interface shear develops. So this is a shear which is acting across this thickness about this particular direction. So you see, there is no shear about this, about the top over here, but it's only acting about the wall, right? Now what can we derive from that? And also, if you take a similar element on the opposite side, is essentially the same. You have a F plus df over here, F over here, and here this df acts on this thin thickness over there. This F is not at the top, remember, although you may be mistaken from the figure. It is not acting on the top surface, but on this thin section. It is acting over this thickness T across this face, across the face which is on the other side of this figure over here. Similar to what was acting, it is acting on this face, this df, and on this side is acting on that opposite face that you have over here. Now what do we get out of this? And maybe you are already getting a hint of how the shear is going to act. Now, so you see here, if this shear, so this is the force. Now if I convert the force, if I go from the force to the shear flow, essentially Q over here, if this Q is acting over here, or the shear stress, so Q and tau, all of them are related. Q or the tau is acting over here, because of complementarity you will have a shear about this direction over here. Similarly here, if your df is acting on this face, because of complementarity you will have a shear force or a shear flow, or the tau, which is acting something like this. So what does this lead to? It leads to some very important conclusions. First one is that as we said, the top surface is free of any forces. So if this is negligible, right, you see this is negligible over here. If that guy is negligible, so that means the complementary vertical shear, that is also negligible because it's complementary. Shear is complementary. Whereas here, this force must be appreciably large to resist this difference of the forces. Remember, these forces are maximum at the top when you're subjecting it to this moment m and m plus dm over here. It is appreciably high. This shear force is appreciably high, and because of that, the complementary shear is going to be appreciably high as well. And this is what it shows you, that this and this arrow are appreciably high. Okay, so what you see that in the web, the shear, actually the shear flow or the shear force is acting along this, is acting parallel to this element over here. Take a look at this arrow. This particular arrow is acting parallel to this face over here, right? Okay, so that takes care of the flange. Now what happens in the web? Let's take a look at the web. See, in the web, as I said, that on this face of the web that you see, there is no shear, right? So that means if you take a web element, this side which corresponds to this side over here, this side is, the shear is negligible because, simply because you do not have any force which is acting on this face over here. So since this is almost zero, this is also going to be zero because of complementary, right? So in this case, which is the force, or which is the direction of the shear flow or the shear force or the tau which is resisting your stresses? Yes, these are these ones over here. So if you take an element in the web, in that case, these guys over here, that is q is negligible, so this is 0 and this horizontal q is almost 0, whereas this is appreciably high and this is also, the vertical shear is also appreciably high. So you see that in the web, the component of the shear which is appreciably high, it acts vertically down, essentially again parallel to the surface of the web, right? So here it acts parallel to the flange and here it is acting parallel to the web over here. Now let's go ahead and take a closer look into this one. Now we understand that what is the direction of the flow of shear which is happening in the flange as well as the web. So if you take these individual elements, this is the flow of the shear that is happening, or essentially q or tau if you want to call it. Let's stick with q over here because tau and q are related. So if you take these small elements over here, you will see the flow of shear happens like this. So q, it essentially, it acts parallel to the element side. So at the top, so this is very interesting. It may appear a bit non-intuitive, but now that you have understand that where, along which faces the shear is appreciably high, along which faces the shear is appreciably low, now you can understand that the q is appreciably high and it acts mostly parallel to the element faces. So in the flange, it is acting parallel to the flange. In the web, it is acting parallel to the side of the web, which is over here. So it is acting vertically down over here, acting horizontally over here. And note the directions. I will come back to these directions once more. So essentially, what do we get? If we now take a zoomed out view of this entire thing, what you essentially have is a shear force V, which is acting across this entire section. Because of the shear force V, interestingly, what you have now, that the shear flow or the shear stress in the flange, remember the top part is the flange and this is the web and this is the flange again. In the flanges, the shear acts parallel to the sides of the flange. In the web, it acts parallel to the side of the web. Also, one more important thing which also will make you think that why is this known as shear flow? Why is this word flow? It is essentially like the flow of water. If you think about it, if you are pouring water from the top, right? Imagine this V, instead of being a force, it's like you're pouring water from the top. The water must accumulate from everywhere, go down, and it must disperse out. So this is exactly what is happening. When you're pouring water from the top, water is coming from the sides, and from the top it is coming over here, and then water is flowing out. So it is just like the flow of water. And you will see, instead of I sections, if you take some of the other sections, depending upon the direction of the shear flow essentially follows the rule that it is parallel to the sides of the faces, and also it is analogous to the flow of water. Water must come in and it must flow out in the direction you're pouring the water over there, right? So now that we have kind of understood that how the shear flow happens, now the question is that what is the magnitude of these arrows? Remember, for the rectangular beam we looked at, the magnitude of the arrows were very small at the edges, higher, towards the center, and again negligibly small at the bottom part over there, right? So now here the question is that what is the magnitude of these arrows? It is going to be, is it going to be very high here, low here, high here? I don't know. So let's go ahead and take a look at some of the cases where we find the magnitude of the arrows. Now before we go there, this is what I was telling you, that this is how the flow of shear happens. We just discussed the I section over here, but this is again, as I told you, it is like the flow of water which you're looking at, right? So if you're pouring water from here, water goes from here, so this is the V, direction of V. It coincides with the direction of the flow of water. If you're pouring water, it goes from here, goes out from here. If you're pouring water from below, the water accumulates from the bottom and then goes up. Similarly over here, we're pouring water from the top, water must come in from somewhere, from these edges, then it goes and then it flows out here. Similar for the other sections that you see over there, right? Now for the I section that we looked at, right, for this I section, so this is what it is. So if you have this force P, which is equals to V in this case, say, right, because this is applied shear, right? How does these arrows which we looked at in the previous slide, how does the magnitude of the arrows change as we are going from the edges to the center of the flange, to the web, to the bottom, to the middle of the web, and all the way to the bottom, and it flows out? So let's go ahead and take a look at the derivation of how this Q or the tau essentially varies. So we have seen that for this kind of a I section that we have, when it is applied to a shear, which applied to a shear force P. So let's say in this case your P is nothing but equals to V that you see over here. The flow of the shear happens parallel to the element side, and it is also like the flow of water. So if your V is acting vertically down, you are going to have the overall dimension. So let me just quickly mark it. It is going to happen something like this. So parallel to the sides of the flange at the top, and parallel to the web in the middle, and the flange again at the bottom. That's like the flow of water, it just flows out, right? Now what we are trying to find what is the magnitude of this Q. Is it going to be maximum at the ends and maximum at the centers and so on? So let's take a look. So for this, you have this cross section over here, right? Now here, remember that since the sections are thin walled, since the thickness is usually very thin, usually most of the dimensions are marked center to center, because the edge dimensions are essentially very small. So that's why you have a h over 2 over here. So we are going to start in deriving this formulation first for the flange. Now remember, the flange is this top part over here. So this is my flange, and of course this guy is my web. So first, if we start with the flange, so what I'm going to do in the flange, I'm going to take a small chunk of it, so along essentially this section BB. So my section of interest is this small chunk that you see over here, similar to something like this over here. So if I take this one, you see this small yellow portion which I've marked over here. I'm just trying to find that what is the the arrow that is over here, what is the Q which is going to act over there, what is the magnitude of that Q, that is what I'm trying to find. So essentially my section of interest is this one, and I'm trying to find that at this edge, that where I have drawn this section BB over here, what is the value of the Q that I'm getting here. So Q may be in the flange, Q or tau in the flange, what is the value of that I'm trying to get, right? So let's go ahead and try to write that one over here. Now you see, to find this Q, remember that our generic formula. So if I write it out, I have the Q of flange is going to be V Q divided by I. Now I is a property of the section, so I'm not going to tinker around with that. V is the applied shear. So the element of interest is this guy Q over here, right? So the Q is essentially, since this is my section of interest, remember Q for this particular section that I get over here is simply going to be equal to the area of the section. Q is A prime times Y bar prime, the area of the section A prime, and Y bar prime is the distance of the centroid from the neutral axis, which is h over 2 over here. So let's just write it out, that what is my Q going to be. So Q in this case is going to be the area of the chunk is S times this thickness TF over here. So it is going to be S times TF, right, times, so this is my A prime, times it is going to be your H over 2, right? So this is Y bar prime. Okay, so now that I have this, let us put it back in the formula and see what it comes out to. So I have my Q of F. If you do a slightly a bit of rearrangement, so what you will get is that S P of F H V over 2I. Okay, so this is my formulation for the Q of. See that one particular thing, note that this is a function of S. So what does it essentially mean? It essentially means that at the edge where S equals to 0, Q equals to 0, and it slowly peaks up as you reach towards the center. Now since this is a doubly symmetric section, doubly symmetric meaning that it is symmetric about this axis, symmetric about this axis over here, it actually suffices to just look at 1/4 of this one over here. So we'll just do it for 1/4. So here you see that S is 0, so Q equals to 0, and it slowly peaks up and becomes a maximum at this particular point over here. Now for this one, if you're going from this side, you essentially have to replicate the similar kind of an exercise. So here let's just go ahead and maybe mark this one. So this is my value of Q of F that I get. Now remember, what is the relationship between Q and tau? I know that the relationship between Q and tau is that my Q equals to your tau times T, right? So this is the relationship we know. Now since we're looking at the flange over here with the thickness of TF, so your tau of F, so that is the shear stress in the flange, it is going to be related to the Q in the flange that you see over here. So this also essentially gives you the relation that your tau equals to Q divided by T over here. So if I just write it out, that tau of F, right? So my tau of F is going to be Q of F divided by the T of F. So essentially this T of F goes for a toss over here. So what you get, the simplified relationship as S H V divided by 2I. So this is the shear force which you get in the flange, which is over there. Now note that, very important, note that, and we will mark it out, we will draw it out later. Note that the value of the Q and the tau both is essentially 0 at the edge, and it also makes sense in certain perspective. I will tell you why. So if you see at this guy again, you see here I don't have any shear at this particular face, right? So that essentially means that this complementary shear must also be 0. So it's that's what you get exactly at that particular edge. If you see exactly at this edge over here, the tau is 0, Q is 0, and as you slowly go in, it is a linearly varying function of S that you see over here. Okay, so that takes care of the flange over here. So it is going to go from 0 over here to have a linear increase. So if you have to draw the magnitude of Q, let me just magnitude of Q or magnitude of tau. So let me try to sort of roughly mark it. So it is going to go from 0 at this edge to a maximum value over here. So this is just the magnitude, not the representation of the direction or so on. Similarly, for the other side, you are going to have a 0 over here, and it is going to peak up to something over here, right? Okay, now let's come to the web. Now for the web part, let's write the web. Web is the vertical portion that you see over here. Now for the web, suppose if I'm trying to find the Q which is acting over here, remember for the web I know this Q is acting vertically down. So for the web, say if I try to find the Q exactly at the interface over here. So if I'm trying to find the Q of the web at this interface, right? So let's maybe make a note that so at the interface with the flange. So if you take that one over here, similarly you have the Q of F equals to VQ divided by I again. Now so let's just maybe go ahead and write that first, the generic formula. Right now you see in this particular case I'm again not going to touch my V, not going to touch my I. Now Q, what does Q happen? Now since I'm calculating over here the entire section above, it encompasses, it comes. So it's essentially wherever you're trying to calculate the Q, whatever section you have left behind. So here you're trying to calculate it over here, whatever section you have left behind was this one. Here since you're calculating here, whatever section you have left behind is essentially this, the whole of the top part over there. So let me make this figure maybe a bit more messy. So essentially this is the whole thing which you're looking at, right? So for that one, if you compute, so here your Q is going to be what? It is going to be this entire area, that is S times this, so S is going to be, so this one over here, so this is this whole thing, so that is the width of the web, that is B times TF. So Q is going to be B, sorry, yeah, let's color is fine, B times TF. So this is the area, and the distance from here to, you know, to the neutral axis. So since this is a very thin walled section, this distance can be taken simply as h over 2, that is fine. So BTF times h over 2 that you get over here. So now if you back substitute in this one, what this expression essentially gives you is that your Q of W, but remember this is at the interface between the, with the flange. What you get is that B times TF times H V divided by 2I, right? So this is the value of Q that you get at the interface. Now if you go a little bit further down the section over here, instead of calculating here, if you calculate it slightly below, at the, exactly at the over here, so exactly at the centroid, you can derive. And if I take a distance R, and a similar way I try to derive, and you can take a look at a textbook of how to get that one. I'm simply going to write the formulation over here, since you know already how to derive these formulations. What I will get, that at that particular point, I think I did one mistake, because no, this is fine. So this I wrote QW over here. Now in this case also I wrote your tau of the front. So for this correspondingly at the interface, if I write at the tau of the web, how does this look like? So tau at the web, remember, is Q divided by T, but here my T, the tau at the web over here, is this thickness over here, that is the TW. So how is this going to look? Is this going to look like? So it is going to be QW divided by TW. So that essentially becomes equals to B TF HV by 2 TW times I, right? So this is the shear, but again the shear at the interface between the flange and the web that you see over there. Okay, so now this was at the interface. Now as I was saying, if you come to the centroid over here, the value of the Q and the value of the tau, I'm going to write it, I have it, you know, derived here already. So the at the middle of the web, the value of the tau W, it comes out as something like this. So at middle, and you can derive this easily, middle of flange, at middle of web, at the middle of web. So that is at C over here, at, you know, this particular point. If you calculate it over there, your tau at web comes out as, this is a slightly elaborate formula, so I'm not going to go into the details of that, BH TF divided by TW, and you will see it boils down to the earlier formula we derived. I'll show you in a minute. Plus H square by 4 minus R square times V divided by 2I. So this is the generic formula, and you see that it's dependent on this R over here. Now as I was saying, if you are putting R equals to H over 2, that is if you're trying to derive, you know, the shear, if you put R equals to H over 2, that is you're trying to derive the shear at this particular point, you see it becomes H square by 4, this one cancels, and eventually it becomes BHTF V divided by 2ITW, which is essentially this one. So this is was at the interface. So this is the general formula which you can derive, or you can derive the one for the, you know, interface here separately, right? So now putting everything back together, so let me show you maybe a cleaner page where all the formulas which we derived are already written out, so which is something like this over here. So what we derived, that at the flange over here, right? So this is the, you remember the magnitude which we draw. We did not draw this one, but now it will be clear to you. So you see at the flange over here, it is SHV by 2I dependent on S. So at the edges, it is going to be 0, and it is going to be maximum at the center over here. Remember, once again, it is extremely important to note that these are representations of magnitude, not of the direction. So it just means that 0 over here, maximum over here. It does not mean it is going vertically down. At the flange, it is acting parallel to these edges over here. Okay, so this was the for the flange. And if you take a look at the web over here, right, at the web, this is what we derived. This is the same formula which we derived. If you just remember, BHTAV divided by 2ITW. If you just go back, this is essentially what BTHV divided by 2T W times I, which is exactly what you have over here. And this is the Q of the web, right, at this interface, at this particular place. And at the center, this is tau W. We can derive a QW at the center as well. It is not just not done over here. So this becomes the maximum at the middle of the web. Why it becomes the maximum? This again takes you back to the concept of that rectangular face which we were saying. Remember, it is minimum at the top and the bottom, and it is maximum at the center. We had done a similar example for this one, in which also you had looked at a I section, but that I section was not a thin wall. It was a slightly thicker wall I section that we looked at, right? There also, if you remember, there was a jump over here, and then we reached the maximum thing over here. Now here also, remember, this ordinates that you see, it is only representative of the magnitude. It is not representative of the direction that you have. So maybe it's better to explicitly write this down. So what you see over here, these guys are only so this represents only the magnitude and not the direction that you see over here. Okay, so what I want you to have a takeaway from this, instead of remembering all these numbers and so on, because you can easily derive. We'll do a problem example where we derive this, is that the shear flow, it happens parallel to the edges over here of the flange as well as the web over here. Now also in the flange, it is 0 at the edges and peaks to the maximum at the center. At the flange also, it is the minimum is at the interface and it peaks to the maximum at the center, and the flow is just like the flow of water that you see over here. Okay, so now let's again make a note. So this is what I was saying. And also one very interesting point that you will realize here. You see that this is just like the flow of water which I was saying, this V over here. So you see at this particular point in the flange, so this, if you're pouring water from the top, right, it comes over here, and this one, it merges. This water comes from here it merges. So here the volume of water, analogically the volume, quote unquote volume of water, must have both this one and this one. So it must be Q1 plus Q2. So does it happen in our case? Let's take a look. So here you see at this particular point, which is at B over 2, which we derived, right, where S was equals to B over 2. So let's go back to the previous page. See, at here S was equals to B over 2. So if you put this guy back over here, what is this ordinate that you get for the Q? So the ordinate for the Q that you get is that, I will write it over here, that Q at F at B over 2 becomes equals to, so if I put S equals to B over 2 over here, so that becomes B H T F V divided by 4I, right? So what I am saying, that here the magnitude of this one, of this arrow just at this point at the center at B over 2 is this one. The magnitude of this arrow is over the same. Now if this is just like the flow of water, if these two have to mix together and flow into this one, the magnitude of this one must be twice, because these two are equal. The magnitude of this must be twice, right? And for this one, at this region at the web, we have already found this one. You see, the magnitude of this one is exactly twice of what you have over here. This was BH2FV by divided by 4I. If you multiply with 2, this you get BHTFV divided by 2I. So it is just like the flow of water. This is essentially what it shows you over here. Q1 and Q2 here, both are the equal in magnitude. So these two are the same over here, and both of them sort of merge together, and eventually this Q which you get at this interface, it becomes equal, right? So, and also one important thing you note from this magnitude, or from the length of the arrows itself, it is very negligible over here. You have a smaller arrow at the edges, it peaks up at the center. These two arrows, the length of this arrow is essentially the double of this one, because it sort of merges together. And here at the center, this tau or the Q is maximum. So you have the biggest arrow over here, it reaches back over here, and essentially the water flows out something like this. right? So overall, to note is that, so this is the nutshell, that the shear flow, it has linear variation in the segments which are perpendicular to V. So this is the V over here. Oops, sorry. So mark that accidentally. So if you have this V over here, this is the section which is perpendicular to V. That is the flange over here. Here the variation is linear. You see, it starts from 0, it linearly varies, whereas in the section which is parallel to V, which is essentially the web, the parallel to V, you have this parabolic variation over here. Here also it is minimum at this interface, and it reaches the maximum over here. So now that we have an overall understanding of how the shear flow essentially happens, let's go ahead and take a look at a problem example. Maybe not an I section, we'll take a look at a box section, a box beam that we have. So to make these ideas more clear, we are going to draw out what is the variation of Q, what is the variation of tau for that particular one. So hang on, we'll go on to the problem example. So you see the problem example on your screen. What it essentially has is a box section, a thin walled box section that you have over here. And in this one, this is this is subjected to a section shear of 10 kilopounds or 10 kips over here. This is essentially the same section just drawn in 2D that you have, right? Now what you are asked is to find the variation of the shear flow Q. So essentially how Q varies across a section. Now before trying to solve this and trying to find the numbers from based on what we learned, right, how do you expect the Q to vary? So again, remember, it is just like the flow of water. So if you are pouring water from the top over here, the water has to go from both the sides through the walls and then has to come out from here. So what you can vaguely imagine is that the flow of the shear is going to happen something like this, right? So this you can imagine as the flow of shear is going to be. Also, one more thing, remember that for the faces which are perpendicular to the direction of the shear, the variation of the shear force is linear. That was one of the things we concluded, right? Also, in the face which is parallel to the direction of the shear, you must have the variation is parabolic. So what you expect to see, and we'll see if we come to that kind of conclusion, is that in this phase maybe it becomes something, the variation will be linear. Remember, so again a representation of the magnitude, not the direction. And in this phase maybe you will have a variation which is kind of parabolic like this over here, and the remaining, and it will be same for the other phases. So for this phase also you should have something like this over here, and then for this particular phase you will have something like this, and for the bottom one also you can expect to have a similar kind of a triangle which you had at the top. But anyway, so if we take a look at this problem and try to solve it, which is over here. And also one more thing, remember one more important thing, that this guy that you see, since it is like the flow of water, here at this interface over here, the water which is over here must come down to the water over here. So whatever the Q that you will get over here must be equal to the Q over here, right? So we will see if we get that thing as well. Okay, now let's take a look at this section. So this is the box section which I said in 2D. So let me again, so here also the top part is the flange. Let's make a note of it. So this is your flange, and this guy is your web, right? Let me scroll down a little bit maybe, so to have these things clear. Okay, so the flange and the web that is there. Okay, so let's start with the flange. So in the flange, so this is the shear force which is acting throughout. So in the flange, if I take a small section, if I take a small chunk, maybe up to here, right? Again, since it's a doubly symmetric section or a symmetric section, just doing 1/4 maybe is sufficient. You know how the variation for the rest is going to be. So if I am taking a small chunk which is say at a distance s from, similar to what we did before, say let's say this guy is at a distance s from here, and I'm trying to find what is the value of the Q in this particular Q in the flange, right? So if I have to find that one, so I'm writing the flange over here. Right. So the Q of flange is, again remember, it is VQ divided by I, right? Now you have I for this section is given. I will tell you what the I is. The I for the section is given as 179.7 inch raised to 4, right? So you're given VQ by I. So you know the V is the 10, you know the I, this is known, so I is known over here. Now what is the Q? Again, Q is the section you have left behind, so we are going to have to calculate the Q for this area which is over here. So let's write the Q for that one. So for the Q, and here also one more thing to note, these dimensions are marked center to center. So you see this is given 3 and then 1 and 1, it is just 6 plus half and half, so that is the 7. So it is okay for thin wall sections if you're just dealing with the center line dimensions that is there. Okay, so for the Q, it is going to be the area of this one over here. So that is S times this thickness. This thickness is also given as 1 inch. You have a 1 inch thickness overall, so let's mark that thickness also. So the overall thickness that you have is 1 inch over here. So the Q that you get is S times 1, right? So that is the area. Remember, that is the A prime, and then you have to multiply with the Y bar prime. The Y bar prime, it is in center to center, so Y bar prime is half of the 7. So this is the neutral axis, this is the center line dimensions which are drawn over here. So this is the neutral axis, so your Y bar prime, it is going to be 7 by 2, so that is 3.5.